Oh, that's great. Thanks, Sergey. So I'm just gonna get started. So I'll be going over some examples of using deep convolutional neural networks today, especially for the UNet architecture and the masked RCNN architecture. So while I'm going over the presentation, we'll be using a web-based GUI to do some labeling as well. And I encourage all of you to make an account on that. That's CVET, and I just threw the link in the meeting chat. So while I go over the presentation, please make an account on that. And then once we go over the hands-on bit, then you can go along with it to actually do some labeling of your own. And also, I'm also going to so I'm going to copy this link, and so this is the, let's see. It's much better. So if you follow this link, then you can go onto today's lecture folder, and you can find this presentation as well as all of the notebooks that we're going to go through and all of the data in that folder. And then you can also follow along. So without further ado, let me get started. So hi everyone again. My name is Tommy, and I'm a student of Sergey and also Maxim, whom you've also heard in previous lectures. So my research interests are in machine learning and deep learning, especially applications in computer vision in analyzing microscopy data, and also specifically in systems related to radiation damage, say, for example, in nuclear reactors. And my background was in nuclear engineering as an undergrad, and I'm currently in a PhD program in the energy science and engineering, but with a specific focus in material science. I'm with the Bredesen Center here at the University of Tennessee, which is a joint program between the university and Oak Ridge National Laboratory. So a little bit of a background. I started doing machine learning when I was an undergrad, and that was back in 2017. I actually started out also doing really basic, fully connected neural networks using the attendess data set, which was also discussed in previous lectures. The data set with the numerals basically, and I started doing out in biostatistics and on R, no less. So the field has advanced a lot by now, and everyone's doing it on Python, and so yeah, it's been really exciting to see how far it's gone. It's evolved through all these years. So so on today's topic, we'll be going over different methods of segmentation in identifying microstructural defects, and in electron microscopy. For my data, they will be coming from transmission electron microscopy, but it applies to all sorts of microscopy data from STM or SEM or STEM images. And just as a reminder, segmentation just means that we're associating each pixel in an image with a class. So for example, in these images, there are different kinds of defects that you might observe in a TM or STEM image. So for example, cavities of all sorts, bubbles and voids. And you can also identify precipitates and and there are dislocation loops, for example, or different dislocation lines, and all these sorts of defects can be identified automatically using various architectures of convolutional neural networks or deep convolutional neural networks. And for different types of segmentation systems or architectures, you will probably use slightly different versions of labels, which as we've discussed before, you'll need a few training data, which are labeled data by a domain expert for training before the network can start identifying other features automatically. So in semantic segmentation, which basically means you get a single mask of all the features you want to identify quite accurately for a single image, for example. You will use one-hot encoding. What that means is basically you'll have, for example, in this image, there are both precipitates, which are these smaller white ones, and the larger ones, which are voids. To identify this image for the label you're feeding into as training data for the network, you'll have two sets of labels. So the first labels will concern the precipitates alone. So basically you'll circle out all the precipitates as one single image, or one single mask as it's commonly known. And for the second mask, you'll have all the voids, and they won't appear on the same mask, but you'll feed both of these masks as one set of training data for the network. So one-hot encoding simply means you identify each feature that you want to identify, for example, the precipitates, with a value of 1 for the pixels associated with the features, and the background would be 0. So for voids, you would do the same, and that's why you have two separate masks. And that's particularly useful for one-hot encoding, which is most commonly used for UNet architectures, which we'll go over real soon. Now, for other identifying systems, you will probably use some kind of a bounding box. For example, in a YOLO architecture, which we won't cover in this lecture, but it's also used especially in video analysis. You'll just draw a bounding box, but it doesn't give you that segmentation that's achieved by UNet, which identifies which pixel in that bounding box, for example, so it's associated with a feature and which pixels are the background. So combining semantic segmentation and just simple bounding box object identification, we get instance segmentation, which we're also going to go over, for which uses a different architecture called Masked RCNN. For that to train, you'll give the bounding box for the objects you want to identify, and you'll also give the mask of the objects you want to identify, and you'll give a mask and a bounding box separately for each object or feature on this image. So for example, there are about 10 these are bubbles, so about 10 bubbles on this image. You get 10 of these masks, and each mask will have its associated bounding box surrounding each bubble, and also a label for the class. So for example, here we only have bubbles, you'll only have a single class of all the bubbles. But for example, if we apply Masked RCNN to this image, which shows both precipitates and voids, you'll have two classes. So that's why it's kind of important to keep in mind the different labeling schemes that we need to we need to apply for different architectures, because they're slightly different, but it's easy to use a graphic user interface, typically web-based, to generate all these labels and convert between one another. I'm going to show you a little bit in a few slides. So there are a lot of these tools out there. and it might be confusing to pick one to use, but today we're gonna stick with CVAT, partly because this is the one I use, and also it's developed by Intel, so quite a number of people use it. But at the end of the day, they all perform the same function, so there's no harm in picking the one you want that suits you the best. Okay, I see a question about the defect segnet. So I'm not using the defect segnet specifically, but if you shoot me an email afterwards, I'd be happy to see what could be done about the compatibility problem. The UNet that we're using right now that will be covered is actually an implementation in Atom AI, which was covered in previous lectures by Maxim, who developed the software. So yeah, I'd be happy to answer any questions afterwards as well. So going back to the GUI interfaces, so we'll go over this how CVAT works, but as I've mentioned, other systems work equally fine as well. So before we actually do the demo, I just want to quickly go over the workflow for using CVAT, which is also typical of other labeling systems. So one important tidbit before you start labeling, for most applications, especially for electron microscopy data, since the size of the image is pretty much set, which is what you get from the microscope, you want to just like make sure and make certain that all your images that you're trying to label have the same dimensions. So for example, 1024 by 1024 is a typical size. They're typically square. It just what tends to work better if your images are square when it comes to doing training on deep convolutional neural networks. And so after that, then you go over this workflow whereby you start by creating a project, and then you create a task out of that project for a single image, for example. Then you do the labeling, and then you export the labels. And typically the labels aren't exported as a mask. They're exported as, for example, an XML or JSON file, which gives you all the points you need to recreate that mask. And then you will use Python to parse those exported labels to actually generate the mask that suits your needs for the different architectures that you might be using. And it's pretty easy to create a project and do labeling. So you start by create a new project, a new task, and then click on it. I'll go over this afterwards. And there are several methods which you could actually do the labeling. A polygon tool is pretty typical for slightly more irregular shape. Otherwise, you can use the ellipse tool. And just one thing when it comes to using a polygon tool for CVAT specifically, which I really appreciate, is that you could just hold down Shift, and then as you hover your mouse along the object, it would automatically generate the points. And so it's just much easier, and I find it more intuitive than some other tools out there. And afterwards, you will be exporting that data. For CVAT, it's an XML. For some other tools, it's JSON, but it's pretty similar. If you look at this example here, you see all the points which refer to these vertices you've just drawn for the polygon. And so then you can just use Python to like parse these labels, the mask from these labels. So just a few notes before we begin labeling. So typically features have a convex mask. So for example, they're typically elliptical or straight or circular. Especially for defects such as precipitates or cavities or voids or all that kind of defects that you might observe. And it just works better when it comes to using when it comes to performing segmentation. So if you identify a concave mask, so for example, if an edge is sloping inwards, you might want to reconsider it and see if it's an occluded mask. So it might be just overlapping objects, and you want to depending on the network you use, you either want to identify two occluded objects as one single object or overlapping objects, or you want to identify them separately as two convex objects. And don't leave holes between overlapping masks unless unless you actually see them, because the network just performs better if you have one nice big object. And also just keep in mind the output files from different labeling systems. For example, you might do conversions from XML or JSON. For this tutorial, I'll be looking at how you can export and parse XML files, but it's the same for JSON files. It's pretty similar. You can modify the script for JSON files. So I am going to go over the hands-on part for the labeling exercise. So just want to get a show of hands. Has everyone been able to register on CVET to create their own account? All right, looks like we've got people who could create their own account on CVET. That's great. So hopefully you could follow along when it comes to using CVET. It's pretty easy to use and pretty intuitive. So let's begin. And I think you're all seeing the screen of my web browser right now, and this is what you see for CVET when you first log in. I have some other projects on here, but basically to start your new project, you just click this create a new project button, and then you could give a name. So for example, DL Summer School 2023. So that gives you a new project, and you could and one important bit here is to actually add in your labels. So you could name them whatever, and for our purposes, we have one single label for the features for the image that we're using, and it's just bubble. And then that adds the label in, and click cancel. Then you can see that this bubble has been added as one single label. You can add in other labels as well. So then you will click submit and continue, or submit and open, depending. And that creates a project. The project has been created. If you go to the project, now you have a new project here. So just a quick note on the image that we'll be using. It's in this file, this folder on GitHub, and it's the test image.png. So you can download it and start toying with it. And then now that I have a project, I can start adding the images in. So I can click this create a new task, and I can name it test image, for example. And this is actually where you add in the image. So I'm going to drag in the image from my local device. And so if you download the image, you could do the same as well. And that adds in that adds the image into the task, and you can just click submit and open, and you just to wait for the image to upload, and there you go. So you already see a job here. So you can click on this job, and that gives you the actual GUI for labeling these images. So as I've discussed before, there are multiple ways to do this labeling. For example, a simpler way is to hover over draw new ellipse, and you can start by pressing either shape or track. I typically click track, but the difference is minimal. It's just that if you click track, it gives you an additional parameter that allows you for more advanced networks to actually track the objects you've drawn. So for example, if you have a time series data and your feature moves along, then there's an additional parameter that facilitates that tracking. When it comes to labeling, and also when it comes to doing the training of the neural network, but it doesn't really matter for our purposes if we're just doing it for separate still images. So now that I have the ellipse, I could try drawing a label, for example, for this circle here, this bubble. So you just drag on one corner, and then you can adjust by pulling the vertices. And if you don't like what you've labeled, you can just press delete, and that tells you to remove the object, and then you can just click yes. And then you can hover over, and then you could so you could start again by pressing track. And then you could label it, and you could create the label again. The other thing is you can also use polygon for more irregular shapes. So again, I'll press track, and say, for example, I want to label this object. So if you scroll your mouse wheel, it will zoom in, and then you scroll it the other way, it will zoom out. So zooming in might be easier. So as I've discussed before, you could either just click on the vertices, which is might not be accurate. And if you want to backtrack, it's really easy. You just click the right mouse button, and there you go, and that backtracks all your vertices. So the easier way of doing polygonal labels is to just press shift, and then you can start hover over the shape you want, and that automatically generates the polygon. And when you're done, you can press N, and that generates the shape. And if you want to if you want to do another label, then you press N again, and you hold down shift, and then it will give you, and then you can draw another label for whichever bubble you want to do, or whichever feature you want to label. So for example, this looks like an occluded object potentially, so I'll probably do something like this, and then to the best of my knowledge, I will generate that overlap right there. So has anyone been able to do their own labeling so far? If you could raise your hand, if anyone is able to do that. or if you have any questions, I'd also be happy to answer right now. All right, so let's say you're done with labeling this image. So how would you export it? And that's pretty easy. So first you want to save it, because I do not think CVET saves automatically. So is there any limitation about the size of the images? To my knowledge, I do not think so. Yeah, I don't think so. So I guess one thing is that since the pixels for each object that you've labeled is associated with the actual pixel on that image, if you resize it afterwards, your mask might also need to be adjusted when you generate it in Python, because it might not take the resizing into account. So you probably want the image to already be in the size that you want to use for training before you actually do the labeling, instead of resizing the image afterwards. But yeah, I don't think there's a limit to the size to the image. Maybe if it's too big, then it might simply fail to load, but I'm not too sure about that. For instance, this image is 512 by 512, which is on the smallest size for images. So so going back to how to export these labels, you will click save to save your annotations, and before you close the web browser, it's also it's just advisable to save your labeling before you close, or if you're gonna be away for a while. And in menu, you could select export job dataset and give it a name. I'll call it test data. If you click OK, and it'll say that the annotations have been exported, and then it's downloaded. And if you decompress that zip, then you'll see the XML file that I've mentioned before. And so so this is basically how you use CVET to first get the XML files. The next step would be to parse that XML file, which I'll go over later as a single workflow in actually performing the classification or predictions using the neural network architectures that we're going to cover. So I'm gonna stop sharing screen and go back to the presentation. All right, so how's everyone feeling? I hope that simple demonstration just kind of shows how easy it is to generate your own data, especially when it comes to, so in previous lectures, I think Yana has gone over how to generate data synthetically for training. Sometimes it's not quite possible. For example, if you have more like these larger TEM data with larger defect sizes, which are not atomically resolution, and so it's kind of difficult to synthetically generate that kind of data. And so that means it comes down to performing your own labeling. But typically you don't have to label a lot of data. Obviously, it's better to have more data, but in my experiences, for similar data, even 2 or 3 images is sufficient to achieve a really high accuracy when it comes to automatically generate the labels using convolutional neural networks. And that could be applied to 30, 40, 100 of similar images. So I think concave features are a slight problem for these distinct defects, but if you have dislocation lines which are a lot more connected, it's not that big of an issue. And there are also other architectures which are more perceptible to or perceptive to lines, for example, or edges, which better resemble dislocations than say, for example, precipitates. So there are other networks out there. The residual the rest head net is one of them, and there are other networks available. So it kind of depends on the architecture of your choosing. So yeah, so at the end of the day, it does matter when it comes to picking the right architecture for your purpose. But UNet should also handle it. Typically, it should be fine. It's just that it might not be the best architecture for detecting, say, dislocation lines compared to other bulk defects. So as I've mentioned before, we typically have a pretty small data set that we're working with when it comes to electron microscopy data. And so there are different ways to well, aside from labeling more data on your own, there are different ways to actually try to enrich that data set semi-automatically, at least using code instead of doing it manually. And so I'll go over some of these techniques, and there's a supplementary notebook in the lecture file that kind of gives you a bunch of examples that you could play with. I won't go over that in detail, but I'll just quickly show it. So get the pointer back on. So just before we actually go over the actual inner workings of how to do that, the rationale for wanting to do data augmentation, which is the term for artificially changing your data or augmenting your data to generate more data out of it, is that if you have a more varied data set, your network is less prone to overfitting, which means that it has a better generalization power, and it could perform detection for a wider range of images if you simply change or modify your data to resemble slightly different data, for example, or out of distribution data. That's one phrase that people use in machine learning. So if you have more varied data, basically, then you can use your network for more kinds of data without necessarily training it specifically for the exact type of data that you have. And it's especially important for microscopists who try to perform machine learning on their data, because microscopy experiments typically yield smaller data sets. Relatively speaking, it's also pretty tedious to label these data sets compared to, say, for example, labeling street scenes for autonomous driving. So one way to enrich your data set is to actually crop your image into smaller sub-images. So for example, this image, which is similar to the one that we use for the labeling exercise, it's a 512 by 512 image, but you can use sliding window to crop this image into smaller images of 256 by 256. So what it does is that you put a square window over that starts at the origin, at the top of the image, and then you move it along so that the image kind of overlaps half of the window overlaps half of the previous window, and just for your information, that distance, that window that moves is typically called stride. So in this case, our stride is 128. This is half the length of that window. And then you could slide that window over that image, and from that you will generate 9 sub images out of one single image. And so you're increasing the amount of data, or at least the amount of images, 9-fold, and you still have quite a number of features in a single image. So that's one way to enrich your data or augment your data. The other way of augmenting your data involves actually performing some transformations on them. So simple ones include just flipping your image, or mirroring it, or rotating it, or slightly zooming in or zooming out. I will say, when it comes to resizing or zooming in your images, it's you don't have to do it all the time, because sometimes if your features are about the same size, then you wouldn't want to necessarily make your features a lot larger than they have to be, because they simply don't exist in your data set. Then it's pointless to include them as data, and it might actually hinder convergence when it comes to training. But I guess more pertinent to microscopy would be to actually adding in different sorts of noises that might simulate conditions observed in different kinds of electron microscopy. So you can add in Gaussian or Poisson noise. You can manually or semi-automatically blur your images by setting a few parameters. You can also add in some kind of a background noise, so that specifically targets the background as opposed to your features, for example, potentially. Or you could change the contrast of your image. You can also add in salt and pepper noises for any data loss. So you see that there are some pepper, which are basically pixels which are randomly set to 0, or salt, which are pixels which are randomly set to 1. You can also add some jitter, which is pretty prevalent in scanning probe microscopy, or scanning different kinds of scanning electron microscopy techniques, which shows that kind of rastering pattern that might be observed during scanning. And all of these noises can be incorporated automatically. And I won't go over the notebook in detail because it's incorporated into the workflow, but just to show you that notebook. So going back to the repo, and it's called data augmentation sub, and it's a Python notebook. And so I'm not gonna open in Colab for now, but just quickly going over it. So this section deals with how to perform sliding window cropping. There are some functions that are already included in the notebook. So realistically, you only need to run a single line, and it will perform that cropping for different neural network architectures. And so from this one big image, you can crop it into these smaller images, which are a quarter the size. And that's the same for masked RCNN images. So one thing you might notice is that the labels are slightly different, because for masked RCNN, these labels shown here are actually a collection of all the labels for the individual bubbles. And so they look slightly different than the UNet one, which is just one single mask for the entire image or sub-image. And for image augmentation, as shown in the slides, there are many different ways to do that, and it all boils down to setting different parameters for the noises. And I've included some comments on the range of noises or the parameters that you can change for the noises. Poisson noise in this implementation, which is from Atom AI, is pretty sensitive. So if you just want to edit, you could just kind of use these values in particular. Otherwise, it might fail to generate. And so for example, this is the Poisson noise, and you can add salt and pepper noise. And all of these noises are added simultaneously, or they can all be added to a single image. So for example, in this case, we added in a few Gaussian noise, and some blurring to it, and then see the effects of combining different noises together to your data. And it's already a lot different than the original image that you provided in. So that further enhances or enriches the quantity of and even the quality of your data set to account for more out of distribution data that you might not have included in the original labels, basically. Yeah, so this is how you perform data augmentation. I'll go over it in slightly more details afterwards, but I'm happy to take any questions before we actually move on to the actual workflows for the two different neural networks that I've mentioned previously. Well, I guess if you have any questions, feel free to just throw it in the chat. I'll also be looking at it from time to time, and I can address it as we go along. Right. So the main part to actually performing these classifications automatically is to use convolutional neural networks or deep convolutional neural networks. These terms are just interchangeable. So it's DCNN or CNN. Deep part basically refers to the network architecture having hidden layers, or quite a number of them. That's why it makes them deep. But they're interchangeable for the most part. And so just a quick reminder of what semantic segmentation is, and showing just a quick example of what could be done in different fields. So semantic segmentation simply assigns a class label to each pixel, and semantic segmentation specifically applies to the entire image. Segmentation is the specific act of assigning a class label to each pixel. And so there's also instance segmentation for masked RCNN, which only applies that to a portion of the image which is of interest to you, or when you train it. And so for these networks, while they're all slightly different, but at its core, they all consist of different sizes of convolutional layers, which was discussed in previous lectures, but we'll quickly go over what they actually mean in a few slides. So here are some examples. So for example, semantic segmentation is commonly used in self-driving. So this is just an example of a car and the dash cam, and it identifies the different things you can see on the road, humans and cars and the road itself. In microscopy, you can identify different features. So in this image or this GIF, it's a GIF of a light microscope looking at tumor cells. So what these green outlines identify, they identify tumor cells as the microscope is going over that tissue sample. And so it's possible to overlay that and perform that classification in real time. It all depends on your purposes. So to just as a quick reminder of what neural networks are in general. So they take an input and it generates an output. So your input will be an image and the output will be the labels. And to get to that, there are neurons that are involved, and these neurons is basically the sum of the input and the weights. And the aim of the neural network is to change these weights until the output matches the desirable outcome. So, for example, if you have label training data, you want the output to match your original labels. So it's just that. And one key piece of the neuron is that there's something called an activation function. The activation function, well, activates the neuron. It's an analogy in biology and neuroscience, but what it basically does is that so if you look at this blue activation function called the ReLU function, if the neuron has a value of 1, then the activation has a value of 1 and the output is 1. But if the neuron has a value that's less than 0, it simply gives 0. So that means the neuron is not activated. And by changing the weights, these neurons can be activated or deactivated as the training goes along, and it simply optimizes the output of the network. And this activation function can be changed. It could be ReLU, or it could be leaky ReLU, or some other kind of functions. So just keep in mind that there's something called an activation function that you could change as a parameter of building the network itself. And so when it comes to convolutional neural networks, the convolution part or convolutional part comes from applications of the convolution kernel, which Sergey has mentioned before in his previous lecture. But just as a quick reminder, simply you're sliding over a square filter, and for that square, each pixel is a neuron. So for example, if you have a 3x3 filter, you have 9 neurons, and you perform that exact same operation that we've discussed previously for each pixel that it's gone over. So so for example, so for example, for this filter, you have these different kinds of weights, so from 0 to 2, and you'll be multiplying by each pixel and you're summing it. So that's your output for this filter, it's 12. And if you move along, then you could do the same operation on each set of pixels, and this is the output of that after you perform that convolution operation. And after you perform convolution, you'll be doing something called max pooling, which simply takes it further downsamples that image. These neural networks typically handle smaller data better than larger data. And max pooling is if you apply a filter to to say this output, then you just take the maximum value from that from that pool, and that will be your output, and that further down sample that data further. So these are just like two major components of convolutional neural networks, and you could change the kernel size for both convolutions and max pooling, for example, and other different parameters as you see fit. And that all changes how your network behave, and these are things that you tweak when it comes to improving the accuracy of your neural network. So here's a bunch of lingo that people typically use for neural networks. And just keep them in mind as we go along, as you'll be encountering them in all sorts of discussions online and offline when people talk about applications of deep learning. The training data is the data that you use for training. It's that simple. Validation data is used, is a separate subset of the data that you don't use for training, and you use validation data to make predictions using the network during training. So once each epoch is completed, you'll perform, or the network itself will perform validation. What that shows you is that you can then compute the accuracy of that prediction using the validation data. And if that accuracy increases, or in other words, the loss of the network, which we'll go over a little bit in the next slide, decreases, then you should continue training. But if after training, for example, like 100, 200, 300 epochs, and you see that the accuracy is not improving, or if it's decreasing, then you should be rethinking the design of your network, or maybe the quality of training data. Testing data just simply refers to the data that you're using for testing the trained network after it's completed training. So typically it will be data that has not been seen by the network before, and typically basically the rest of the data set you haven't labeled. Validation data is also labeled because you need to make that comparison after each epoch. Ground truth just simply refers to the actual labels, so the true labels of each image of each image in your training data set, or maybe you have a validation data set. Well, one epoch is one training cycle, and that consists of passing through the data into the neural network, and then have the neural network optimize its weights based on that one single pass through. That process is computed by backpropagation. Not going to cover here. It's not that relevant if you're simply using the neural network to get your own training data and you're not trying to develop your own neural network. But it's basically a series of chain rule derivative operations, which if you're interested, you can read about it. But that's what one epoch is. It's one training cycle, and typically, depending on the size of network, if it's a larger network, you want to train longer. So maybe like upwards to 1,000 epochs. If the network is simple or shallow, then you can train it for maybe less than 100 epochs even, and you'll still achieve pretty good results. And we're gonna go over it when we actually do the hands-on exercises with the notebooks. Batch size is the number of training images for each epoch. So for example, if you have, let's say if you have 20 training images, then you could set the batch size to be 8. So each epoch, it will simply randomly take 8 of those images and use for training. What this does is that sometimes it's simply not feasible to feed in all the training images at once into your network for each cycle, because you will run out of memory. And so it's helpful to limit the batch size to a smaller number, so that it will take in all the images eventually, but it will take in different sets of images for each epoch. Hidden layer is it's the layers that are between the input and output layers, and it's one parameter that you could typically tweak. So the number of hidden layers determine the complexity of your network, aside from the size of the filters that are in each layer. And the learning rate is basically how big a step an optimizer goes or optimize for each epoch. And it'll become more clear in the next slide what the learning rate does. So to actually perform optimization for the neural network, there are two important parameters that you can change. So the loss function is an important parameter that basically compares the predictions that are made from the neural network with the ground truth, and that's really important during training, because the name of the game for neural network training is to minimize that loss function. So the smaller the loss, the better your neural network will be when it comes to performing predictions, or higher the accuracy it will be. And you want to minimize it. So the loss function that most people use and what we'll be using is the cross entropy function. And specifically for our case, if you only have two classes, say the background and whichever feature you are trying to identify, and there's only one type of feature, you'll use binary cross entropy function, which now without the negative signs, it measures the similarity between the predictions and the ground truth, and with the negative sign, that measures the similarity, and hence with the negative signs, we want to minimize this loss function to hopefully to push it down to 0. And you can see that there are some log functions into it of P of yi is the probability basically of the identification. And so with that log function, if you minimize it, it tends to 0. So that's why we use binary cross entropy, and it's just a very robust loss function to use. And so to actually minimize that loss function, there's another parameter that's being set, and it's the optimizer. So the optimizer controls the convergence of a model by minimizing the loss function. And you control that convergence further by controlling the step, which is also known as the learning rate, as we've mentioned before in the previous slide. So this graphic just illustrates what it's like by controlling the learning rate. So if your learning rate is just right, then it will and this is the loss function basically. So after like a reasonable amount of training epochs, it will tend to the minimum, and that optimizes your network by minimizing the loss function. If your learning rate is too small, that means your steps are too low and they're too small, then it will take forever to converge, but it will get there eventually, but it might take a lot longer. On the other hand, if your learning rate is too high, it simply will fail to converge. It will bounce between that minimum, and it will actually shoot out of that minimum, and it will never converge. So that's why it's important to set the learning rate, which tends to be on the order of 10 to the -2 or 10 to the -3. And you probably want to start with a small learning rate. If it's not going as fast as you desire, then you could increase it. But if you get it to too high, then your network simply fails to converge and it won't work. So now we're getting into the more exciting parts of the lecture, of the workshop. And so and before we begin, does anyone have any questions about just the basics of convolutional neural networks and neural networks in general? And how's everyone doing? All right, I'm seeing some thumbs up, so looks like I'm good to go with semantic segmentation of UNet then. Semantic segmentation, as we've discussed before, is simply if you have a image, for example, this image of a lot of different bubbles, and these bubbles are being generated by irradiation bombardment on the material. In this one is used, it's generated using ion beams to simulate a nuclear reactor environment, and it generates a lot of bubbles, and you probably want to identify these bubbles and measure their sizes eventually, and or at least see the distribution. Then you can use UNet to perform semantic segmentation to basically identify all the bubbles in this image in one go. So the UNet architecture looks like a U. That's why it's called a UNet. It begins with the input layers, and you increase the number of filters as you go deeper into the network. So it goes from 32 filters in the first few levels, and then to 128 in the middle of the network. And what it does is that this first half of the UNet, which is otherwise known as an encoder, it performs the task of looking at salient features. So for example, edges and small variations in gradients of the feature that you're looking for. Then to actually generate the labels that match the size of your image as to be expanded back to the original size by these upsampling layers. And that expands this label back to the original size of the image. One important thing about the UNet is that it features these skip connections. So for example, just by sheer randomness, the network can pass the output of these layers directly across into the second half of the network, which is known as a decoder, and it bypasses the deepest levels. And so what it does is that these skip connections, they concatenate the data with the data that's being upsampled, expanded back upon on. These skip connections preserve the kind of a big picture information, so that they often consider the background as well, or more global gradient distributions or variances. And so with these two different scales of the receptive field, which is basically just how much of that image the network is looking at, with these two scales, then, or several different scales, then the predictions made will be of pretty high quality, as it considers a lot of the different features or a lot of different factors that affect feature finding in this image. And so I'll go over the UNet example, and it's also in that same GitHub repo. So it's called UNet. That's what it is. And it's gonna wait for it to load. And you want to run it in Colab. So click open in Colab. And I encourage you to follow along and click the run buttons with me. So first thing with the Colab, and I'm sure you probably have some experiences with it by now, is to connect it. And you probably want to wait for the connection. So just to make sure when it comes to training neural networks, you want to go to runtime, change the runtime type, and make sure that you're doing it on a GPU. I have Colab Pro, so if you're on the free version, you might have a different type of GPU. But just be on a GPU and you should be golden. You should be able to train these relatively simple neural networks. And so we begin by, you run anyway, you begin by installing Atom AI, which enables the UNet architecture, and it was developed by Maxim. You just have to wait for the download. And then you can import the relevant packages. And here's just a simple function to do normalization of the data, which is you always want to normalize your data before you perform prediction on it. So you normalize it between 0 and 1. It just works a lot better for neural networks. And so here we download our images from Colab, from the GitHub repo. So these images are also in the same repo, and the labels as well. So assume that we've already performed that labeling using CVAT. And then we can just read in the images, and here's one of the image. So it shows one of the images that we use. We have 2 of them. And here, so the idea of these notebooks, just as a preface, is that if you run everything, you'll be able to read in images and perform training and perform the prediction all in one notebook, and you don't really have to tweak anything on your part. If you want to do it for your own data, the quickest way really is just to change the images and the labels in this notebook, and it should perform some kind of training, and then you can start modifying the hyperparameters to your liking afterwards. But as a starting point, these notebooks actually just show you how the entire workflow goes. So there's a code for the parser for the XML file, which is contained in here, and you just have to run it. And then to actually parse it, you just run the cell. And so now you see here's an example for the first image. So you have you want to provide the names of the files for the parser to identify the files. And so what you see is that there are different points associated with for each feature that you label. So these points are the vertices of the polygon. And for if they're not polygons, there's ellipses, it will show like the center of the ellipse and also the major and minor axes. And the parser will also be able to identify the ellipses. And then here are some functions that help us generate the mask and the data set for the unit. And it's just one single line after you actually run those functions. And here we can see the mask for the unit, which as we've discussed before is is an entire mask for the entire image here. And it shows the mask for a single image. So here you see the mask being labeled and compared to the training image that we have. Then we can perform sliding window cropping. You run these functions, and then so these are the masks that we have, and this is the function that performs the actual cropping. It's just one single line again, and you can determine the window size and also the step size or stride. Then we can click on this function, or run the cell to show some of these patches or sub images, and they're interchangeable terms again, which shows you how the cropper accounts for both the image and the mask when it comes to cropping, so they always match. And then we can do some data augmentation as well. So for example, we could add some small amount of noises to it. We'll just use a small amount of noise because frankly, microscopes aren't that noisy usually. So just a small degree will do. Unless your microscope is really noisy, then maybe you should be changing your microscope before you do any sorts of training. And so this is just a single line again, and it just really hinges on getting your parameters for the noises. One thing you can see here is that seed is a typical parameter for a lot of functions when it comes to neural networks. The seed is just it governs the random number generator, and if you have the same seed for all the functions that you use, then the random function should output identically across all runs. So that is just a parameter that governs the reproducibility, basically. And there's another parameter, which is the number of classes. For us, we have one, the class being the bubbles, and you want to change this accordingly if you have multiple classes. And we can show an example of the augmented images here, which look like this, and which I've taken them and post them in the slides as well. And that's why the seed is kind of important. If I change that seed, then they will look differently. So if I change to 2, then they look completely different. So, but if I change it back to 0, then they look just like the ones we observe in the slides. So then now that we've augmented the data, we can actually do the semantic segmentation. So if you complete these augmentation tasks and the tasks that generate the labels separate of this notebook and not part of this notebook, then you can uncomment these 2 cells to actually load in the data, either using wget from for GitHub data, or gdown for Google Drive data, like data that might be stored on your Google Drive, and it's just a matter of changing the functions and getting the right links. But since we've already processed that data in the same notebook, we'll just proceed to run this cell to what this cell does is just specifies the images and the labels for training. And for validation, we're going to use the last two images in the data set just to show the effects. While it's good practice to have validation during training, it's not entirely necessary, especially if you're training, if you're training on data and performing predictions on data that is pretty similar to each one another. So you're really using the neural network to expedite that process, then it's not that necessary to have validation, because you understandably it should perform well enough when it comes to the accuracy. And so just as an illustration of the actual dimensions of the data being fed into the neural network. So we have the images are the first set of so this bracket consists the dimensions of the images, and this one for the length. There's an additional dimension here for the images, because if you have color images, it might have 3 channels here for RGB or other coloring schemes. But for us, we have grayscale images, so we have one single channel, and we did that by simply adding an extra channel, and that's it. Now we can also download some data for actually making a prediction on, and that's the test image that we've just labeled. Then we can plot some of that training data again and see what they look like. So 256 by 256. And here's just what segmentation means. So classification is, this entire thing has a cat, so just shows you what it has. But segmentation, it gives you a pixel-wise classification, basically. And then to actually perform training, we need to instantiate the model or initialize it. Again, we have one single class for the bubbles, and then we can print what the neural network actually looks like. So you see these convolutional blocks, and you see that the number of convolutional blocks increase as the network gets deeper. Then it begins to upsample, and the number of convolutional filters decrease from 128 back to all the way to like 32 and 16. That's the output. Then we could actually start the training. And so, for example, we're training for 300 epochs here, which is training cycle in the Atom AI lingo. And we simply use a batch size of only 2 images, just for simplicity. And this is where you specify the images and the training images and training labels. And we can begin training. And because the UNet is a really simple architecture, it's actually, it takes a really short time to train even 300 epochs. So as you could see, we're already done training at 300 epochs. One thing that it shows is that it shows the loss function as a function of the epoch or time, basically. And as you could see, both our training and test, which refers to validation loss, they both decrease and at the same rate, really. So that means our neural network should be pretty accurate, and the accuracy, which is correlated to the which is inversely correlated with the loss, it's increasing as well, and it goes up to all the way to 0.9. So that's another indicator that our neural network is performing as it should. So now we can actually do some predictions now that we've done the training, and it's just a single line when you do model.predict. And just the dimensions issues, you just want to take the 2 2 dimensions in the middle to actually get the image. And here it plots the raw prediction. So from this test image, we get these predictions results, which already look really similar to like this test image. So something that might be missing might be this bubble here. It's not really identified for whatever reason. Maybe if we train long enough, it will. Or maybe our training data set is just not that robust. We only have 2 images after all. And to quantify how good our network might be, we can use different kinds of accuracy metrics. For segmentation purposes, the most common metric is the intersection over union, which is calculated by, well, the overlap over the union. So the intersection over the union. And that's the most common metric when it comes to determining the accuracy for segmentation problems in particular. So this is, you don't have to write the function for calculating this on your own. You could just get the functions from torch metrics, which is associated with PyTorch, which is the backend of what AtomAI runs on when it comes to doing the semantic segmentation and training the neural network. And you just have to simply run the cell to download it. And if you run the cell again, and the actual calculation is just this one single or these 2 lines where it gets the metric. Just be reminded that your input for using torch metrics, it has to be in tensor, but it really is just this one function that converts your input from the NumPy array into a tensor, and that's it. And we got an IOU of 0.72, which for this short amount of training time is really not bad. And also in particular is because the labeling. So this was done prior to this to creating this tutorial, and so the labeling is slightly it's slightly different than what you might expect from this image. So whoever labeled this image decided to use more blocky polygons or even rectangles and more spherical shapes to represent these bubbles. So that's why your IOU might be slightly off, but they all look pretty similar at the end of the day. So as I've mentioned before, this bubble is for some reason missing. We're not sure like that. We're not too sure why that might be, but yeah. So has anyone been able to follow along with this tutorial and clicking the buttons on it? All right. Does anyone have any questions? Thanks, Julian. That's great. Yeah, so well, I hope that you're able to follow along with this tutorial, because we're gonna go over and switch gears to Masked RCNN, which not only allows you to just get a single mask, but you can also identify these objects individually for further processing. So let me just go back to. Okay, so there's a question. So if you train your network on a certain size of images, can it perform predictions with different size images? So the answer is yes, with a caveat. So it will be able to, so obviously you train your network on smaller images because you don't run out of memory. So for our case, it's only 256 by 256. And And as actually we've demonstrated, we fed in an image of 512 by 512 and is able to identify it relatively proficiently. But the caveat is that the size of your defects should match what you fed into the network. If the size of the defects or features that you want to identify are significantly smaller or larger, maybe like 2 times or larger or 2 times smaller than the features that you fed into the network during training, then good chance it's not going to work, because to the network they look like different features. So the size of the image is actually not an issue. The size of the features is an issue. And so yes, so the size of the features is so if you have a 512 by 512 image and you expand that image to 1024 by 1024, then the feature size will be increased by 4 times because of the square. So that's not going to work. So one step that before you perform the actual prediction is you want to resize it so that the physical size of the features are similar to the ones you use for training. So say if the features that you use for training has like as an area of about like say 20 by 20, you don't want your features to have, you don't want the features that you use for predictions to have like 50 by 50. That would be too large. So yeah, you just want to make sure that the feature size it doesn't have to be the same, but it has to be pretty close. Unless you include larger sizes of that defects in the training, which is what you can sometimes achieve by zooming into your training data, then you can generalize to larger defects as well. But that again depends on your use case. So hope that answers your question. Right. So I will switch back to the PowerPoint for the last okay, so I guess we have one more question. So can you handle that by cropping the original image to maintain a similar relative size? Yes, you can handle that by cropping the original image, or you could do that by resizing your image. So cropping is one way to do it. Resizing is simply, it's like the operation of dragging your image and enlarging it in, say, PowerPoint, but you could also do it in Python. CV2 has a pretty simple implementation, which is also like one line that allows you to scale that image, say from 512 by 512 to 1024 by 1024, or the other way around. It depends on your purpose, but it's very simple to do. And you could also do it for a lot of images at once. So that's another way to go about doing it. And in my experience, that typically solves issues with not detecting features, even though your network is trained to a pretty high accuracy. That resolves most issues like quite frequently. Right. So I hope that kind of answers the questions about the scaling of the image or the size that you should be feeding into the neural network. If you have any more questions, feel free to put it in the chat box and shoot me an email. I'm happy to answer them as well. And so then the next step would be to perform instance segmentation with masked RCNN. This is our final section of the day. We'll spend the next 30 minutes go over it. So what the masked RCNN does is that for an image, it takes in, it identifies a region of interest, so ROI. And from that region of interest, it gets the bounding box that surrounds the region of interest, the class of the objects in that region of interest. It's typically one class. For each region of interest, there are multiple regions of interest in a single image. And for masked RCNN, it also gives you the mask. So it gives you the mask of that image in that region of interest. So the masked RCNN is the development of the fast RCNN, but if you add segmentation to it, you get masked RCNN. And so one way to consider it is to actually look at the loss function, because the loss function, unlike UNet, is actually a sum of 3 different loss functions. So you have a loss function for the class itself. So for us, it's either between the background and the bubbles. And then you have a loss function for the bounding box, which calculates how similar the bounding box predicted by the network is to the bounding box predicted by, or the bounding box supplied by Udring training as the ground truth. And also finally the loss for the mask itself, which is the binary cross entropy function, or the cross entropy function, as we've discussed earlier, which is the comparison between the mask identified in the region of interest and and the mask is applied for training. So one thing with masked RCNN is that you can already, so this is a pretty rough training being done to this to the set of images, and you can already see that these overlapping features are identified. So these are colored differently for each feature it is identified, and you can see that so these 2 bubbles looks like they're overlapping each other, and so are these 2, and you can see that they're already kind of identified. Maybe this one is missing a little bit of the identification, and that could be remedied by increasing the training epoch, for example, or providing better training data. So that's why masked RCNN is really powerful, is that it can identify these overlapping features individually, and then you could perform your own measurements on them, or even perform tracking of individual particles. So so let's get to the final notebook of the day. And that's the masked RCNN notebook. And I also encourage you to follow along. It's just clicking buttons on Colabs, so pretty easy to follow along. So if you open it in Colab, I think you're seeing the Colab screen right now. Connect it. Now for masked RCNN, we're using this implementation directly from PyTorch, so we have to install PyTorch, and also make sure our runtime is in GPU and we're set. Specifically for this notebook, we're using a slightly older version of PyTorch because of some compatibility issues. But as long as you stick with this version, then it should be okay. I'm just gonna run the import modules, and also a function for normalizing. And yeah, so installing PyTorch and specifically for a older version might take a little bit of time. So this is going to take slightly longer than the UNet notebook. Right, and then we could download the training data. Also available in the same GitHub repo. And then once again, we get the images by running these two cells. And we have the XML parser, and we parse the XML files. So there are a whole set of functions which are slightly different for the Masked RCNN. And but it's also just one line. And then we can see examples of the mask generated for Masked RCNN. So you can already see that the masks are separate. Unlike in UNet, you'll have to draw the mask separately for each feature on that image. So for this image, you might have 20 or so masks. And then we can get the data set. And the data set consists of the bounding boxes, as well as the masks that were shown previously. So you need the bounding boxes, the mask, and also the class labels but for our purposes, we only have one single class. So that's easy to handle. And then we can also perform the same cropping for Masked RCNN. And just as a quick note, this function takes in the mask specifically rather than all the labels, including the bounding boxes, but just keeping that in mind, and it takes in the mask, and we'll be able to generate the perform the same sliding window cropping for Masked RCNN. And as you can see, these masks also crop, and this is just an overlay of all the masks in each sub image. That's why, and you can see these overlapping in the brightest spots. And here we generate the mask. Then for Masked RCNN, we'll be defining the data set slightly differently. So first we just make sure we have the right variables, and showing an example training image and also the mask. Then we're downloading the testing data for predictions. So the data set is constructed using a constructor, but you don't have to care about that. Just run it and it will construct it. What you will see is that it will have the bounding boxes, for example, and the masks and the labels all in one single data set, which is a type of Python construct but you don't have to worry about it. Just run it and it will, and the network will train basically. So then we can use this function to get the Masked RCNN function, and we can also download some helper functions which helps with training. Again, they're not that important, and there's not a whole lot that needs to be changed about them. And also a simple transform function which flips those images as we perform training to increase the variability of the data. Right. Now we're ready to kind of actually do the training. So Masked RCNN training is going to take slightly longer because the network is more complex. And so if we run the cell, we construct the data set, and we also construct a data loader, which the data loader goes into the network. But just run these cells and you're good to go. You don't have to worry about it too much. But for example, here you could specify the batch size for the data loader, which is training data. So we set a batch size of 2. Masked RCNN in particular, I would recommend you sticking with 2 because larger batch sizes just takes too much memory for Colab to run. And then you can set shuffle to true, which just means that we'll shuffle the entire data set, and then we'll pick 2 out of the data set as the training is being performed. Then we run the cell to actually instantiate the model. So this is the previous function that instantiate the model. The only parameter that really is worth tweaking might be the number of hidden layers in that model. We use 32. It could be 64. It could be larger. It's a trade-off between the time it takes to perform training and the complexity, which might have an effect on the accuracy of the predictions that are made. So it really depends on the purposes and depends on how complex your data might be. So the optimizer is uses a learning rate of 0.001, and it's an atom optimizer. This line simply says that the learning rate decreases exponentially. So as we've mentioned before, if your learning rate is too large, it will simply fail to converge. So one thing that could be done is to actually decrease that learning rate exponentially by adding just a small little function here, and that learning as your training progresses, the learning rate decreases so that it ensures convergence, and that's all there is to it. It probably will converge without that exponential decrease either. So we're ready to train. I'm only doing it for 50 epochs because it does take a little bit of time to train the Masked RCNN as compared to the UNet, just because it's a much more complex model. So while we wait, I'd be happy to take any questions about Masked RCNN or anything we've discussed before in this lecture or even in previous lectures, if I could answer them. And also, if anyone's been able to follow the collab along, I appreciate if you could let me know so that I know that it's working on your end as well. It is necessary to use a rectangular bounding box because because of the way the network identifies the bounding box, it actually takes in a diagonal of that bounding box. So it takes in the starting coordinate and the ending coordinate of that diagonal, which represents a rectangle. So that's why the bounding box is rectangular. So if your features are circular, your bounding box will still be a box, not a circle. But what it does is that within that bounding box, it will be able to separate out the circular feature by performing that segmentation within that bounding box. So it'll be able to segment out that circular feature pixel wise, and that's why you have the bounding box in the first place, is that it doesn't have to perform segmentation over the entire image. It only performs segmentation within that region of interest. So so it looks like we were able to perform training, and we've completed training. So now we could actually perform the prediction simply with this one line here, and you have to set the model to eval mode first. And then here's the image that we're using. Now let's get some predictions out of it. So so what you notice that's completely different from UNet is that it gives you the features individually. So the way the predictions work is that the mask, so it gives you the mask, the bounding boxes, and also the classes. So we're gonna focus on the mask for now because that's the most interesting outcome for us. So the mask of predictor is in an array where it gives you a number of predictions. The predictions do and can duplicate, but they might be of different quality. So for example, if a prediction is made for this bubble, there could be a second prediction, but that prediction might only be a section of this bubble. For whatever reason, the network decides that also constitutes a valid prediction. But just going back to the structure of the prediction, it's the predictions are arranged in order of a score that's assigned by the network internally. So that score informs you how probable that prediction is, or the fidelity of that prediction. So it's in descending order. So the first prediction is always the one with the high score, and this prediction is pretty spot on for this bubble. That's why it has such a high score, and then it decreases as you go along. And for predictions with really low scores, then they simply just don't make physical sense, or they're just really bad predictions. That's something that you might want to consider. It's something, and selecting the predictions that you want is a parameter that could be tweaked. So for our case, we want to just select predictions with scores that are above 0.7. It's a bit arbitrary, so there's a little bit of a trial and error involved here. But so for example, if we like we could also demonstrate the last, or maybe some later predictions. So for example, if we do this, so as you see, like if as the score decreases, then the predictions are not as good. So for example, this one is still kind of makes sense. It's kind of this bit, for example, and if you, so there are about 59 predictions that it's stated here. So maybe if we change this to 50, then you could see the last few predictions, and they just stop making physical sense when the score is just like that low. And for example, this one might correspond to this bit, which is not really a bubble. So that's why it's kind of important to threshold the scores that you want to use. 0.7 is a good start, maybe 0.9. It's just in this code, it's that kind of helps with the thresholding and selects the predictions with high enough scores. And then we also do an RU calculation to see how accurate our network might be. And here are the results. So RU is 0.65. I guess it's not as good as the UNet, but in part because we've only trained for 50 epochs and the UNet's been trained for 300 epochs. If we train this for 300 epochs, probably will take slightly more time than that. Well, on the other hand, you can see that the predictions themselves, we could actually identify these overlapping features, unlike the UNet. So UNet will give us something like this, which just shows you where the features are, but for a masked RCNN, actually gives us results for individual features. So prominent examples include, for example, here you could see that this bubble is separated from this bubble, or this bubble, this blue one here that looks like a mushroom. I guess the cap looks like it's separate from the stem. So it corresponds to these two bubbles. So that's why masked RCNN is really powerful, because it's able to perform segmentation, which is really helpful when it comes to microscopy experiments, because you want to measure the exact size of the features you're observing. And it's also able to tell these features apart so that your measurements are accurate, and when it comes to both size and also distribution. And furthermore, you could, if you have time series data, you could start tracking these features. So yeah, so that's why we've included masked RCNN in this discussion. And it looks like we have a little bit of time. Maybe we could try to improve that result by training for more epochs, let's say 150, and we'll see how that goes. So I will say it's the main advantage is that it's separating out. So the question is that if the advantage of masked RCNN over UNets, it's only because of the overlapping features. It's one of the main advantages, because UNet simply, if you want to identify overlapping features, you have to do a bunch of post-processing, which is a lot more manual and it's not automatic. You have to use different more basic computer vision techniques to separate out the masks from one another. So that's one advantage. And I guess so with that advantage in mind, it translates to that masked RCNN can be used on time series data or video analysis, because it could it could identify individual objects and then perform tracking on them. So yeah, that's some of the main advantages. The other advantage I could think of is that because UNet considers the entire image in one go, and masked RCNN first identifies regions of interest, it could improve upon on UNet by being less likely to consider background artifacts as defects of interest, because it has to pass through that region of interest or ROI filter. So those background features might already be selected out of consideration, then the downside to that could be that it might be more picky when it comes to features. So it might miss out on some other features too. But that also depends on the parameters of your network and your training data. Yeah, so I guess technically we only have 3 minutes left. It's still running, but if you have time, maybe we could find out if training for 150 epochs might improve the network. But otherwise, I'll be here to take any questions as well, because this is kind of this is all I have for demonstrating the two networks and going over how to actually apply a CNN pipeline to your own data. And I mean, if you have any questions about just training convolutional neural networks or training deep neural networks in general, if I can answer them, or when it comes to labeling, if I can answer them, I'll also be happy to take questions. And it looks like we only have about 25 epochs to go. So I don't know if it'll be completed within the 1 minute that we have until 11. But yeah, thanks for attending today's lecture. It's been great to share some of the networks I've worked on. I think they're really powerful tools uh, in analyzing microscopy data, and also in the material science field in general. And there's been so many exciting developments lately. So hopefully those could be reflected in domain sciences fields in the near future as well. Yeah, I hope these pipelines help with people when it comes to analyzing the data. And it looks like we've actually completed training. And not sure if the IOU has improved significantly. It looks like. So might be a data issue, then maybe this data is simply a little bit too out of distribution. But yeah, this is all I have today. So thanks again for attending.
Thank you, Tommy.
Thanks for hosting, Sergey. Yeah, and there will be another session on Friday. So won't be me, but looking forward to seeing you all there as well.